Hello my dear students, let me start session 3. In this session, first I'll take examples related to vector subspace, then linear span and linear combination. Okay. To work out the examples, we have to remember one rule. I'll read out that rule that you know that we have studied in the previous session. Necessary condition for a subspace: A alpha plus B beta belongs to W, to say W is a subspace of a vector space over a field F, where A and B are scalars, alpha and beta are the members of W. First example. W is a non-empty set. Listen to my words with full attention. W is a non-empty set. We have to show that it is a subspace of vector space over V, vector space over a field F. It is an ordered triple. The condition is x plus 2 times of y means 2y plus z equal to 0. Remember this condition. I need two vectors and two scalars. Let alpha beta belongs to W. A and B belongs to F. Here F is a real field. Since it is an ordered triple, therefore we have to denote alpha as x1, y1, z1, beta as x2, y2, z2. Since the condition is what? First element plus 2 times of second element plus last element equal to 0. That means x1 plus 2y1 plus z1 equal to 0. x2 plus 2y2 plus z2 equal to 0. Let me consider A alpha plus B beta. A as it is, in place of alpha I will take x1, y1, z1. B as it is, in place of beta I will take x2, y2, z2. Multiplying each vector by A, here by B, and adding. And you know that we have to add first with first, second with second, last with, third element with third element. First element from first bracket ax1, first element from the second bracket, that is bx2, ax2 plus bx2, ay1 plus by2, az1 plus bz2. Rewriting the statement. Since the condition, what the condition says, first element plus 2 times of second element plus third element, that is last element, and sum of these should be what? 0. First element, here it is ax1 plus bx2, 2 times of second element plus last element. Grouping, that means coefficient of A x1 plus 2y1 plus z1, coefficient of B x2 plus 2y2 plus z2. We have to replace this bracket by 0, this bracket by 0. Whatever may be the scalar values, that means whatever may be the values of A and B, always we get 0. That indicates it belongs to what? W. This shows that W is a subspace of a vector space over a real field containing 3 elements. Another element, the next example. W is a non-empty set. The condition is, here remember, this condition is always important. The condition is the product of first and second element, that is xy equal to 0. This is the condition. The product of first and second element equal to 0. Similarly, let alpha beta belongs to W. A and B are the scalars. Alpha order triple, beta is order triple. A alpha plus B beta, we get this step, same what we got in the previous example. This step is very important. Very important. See the condition of the example. Product of first and second element. First product of elements. Here the first element is x and the second element is y. Using the condition, that means using the hypothesis, ax1 plus bx2 into ay1 plus by2. If you multiply these two, we get a square x1 y1, ab x2 y1, ab x1 y2, b square x2 y2. Whatever may be the value of a and b, not necessary we have to get 0 always. Sometimes we may not get 0. That indicates it's not a subspace. Next example. W is a set containing functions over a real field, or the condition is f of 3 is equal to 1 plus f of minus 5. In place of alpha and beta, I will take f1, f2. Scalars, of course, same. AB belongs to R. We know that A alpha plus B beta. Here we have to take A f1, B f2 of what? 3. Operating 3 on first, operating 3 on second. This is same as writing, since the scalar multiplication law holds good because it is a vector space. A dot of f1 of 3, b dot of f2 of 3. Using the condition, using the condition of the example, f of 3 is replaced by 1 plus f of minus 5. In place of f1, we have to take f1 as well as f of 2. Grouping, we get a plus b plus f1 of minus 5 plus f2 of minus 5. This is same as writing a plus b plus f1 plus f2 of minus 5. Remember, a plus b not necessarily 1 always. Sometimes it is not equal to 1. Okay, a plus b equal to 1, not always. Sometimes a plus b is not equal to 1. This shows that it is not a subspace. Let me take another example containing polynomials. Generally, we denote the polynomial by p of x. Here, p of x is a polynomial of degree 3. W is a set containing only polynomials of degree 3. Before I write P1 and P2, let me recall an important result. We know that sum of two polynomials of degree 3 need not be degree 3. The general statement is like this: sum of two polynomials of degree n or less than or equal to n need not be of degree less than or equal to n. N may be 3 or 5, 7, whatever it may be. Since it is of degree 3, therefore P1x is a polynomial of degree 3. I will take like this. P1x is a polynomial of degree 3. Let me denote the polynomial like this. It is a polynomial of degree 3 because its coefficient is 3. It is not equal to 0. P2x is another polynomial of degree 3 only. Here I have taken plus 3 as the coefficient. Here I have taken minus 3 as coefficient. If I add these two, what we get? We get a polynomial of degree 2. Okay, that means the vector addition law does not holds good. It shows that it is not a subspace. Please remember, if it is of degree less than or equal to 3, then it is a subspace. If it is strictly of degree 3, then it is not a subspace. Let me repeat. If the p of x is a polynomial of degree less than or equal to 3, then it is a subspace. If it is equal to 3, then it is not a subspace. Okay. Linear combination of vectors. To define a linear combination of vectors, we need a set containing vectors. Scalar multiplication means multiplying a scalar by a vector. The combination of such scalar multiplication of vectors is said to be linear combination of vectors. For example, a1 alpha or a1 alpha 1 for second vector and second scalar, a2 alpha 2 for third scalar and for third vector and scalar, a3 alpha 3. If I add these, if I summing of all these, we form a linear combination of vectors. Okay, let V be a vector space over a field F. Alpha 1, alpha 2, alpha n are the n vectors of V. Then the vectors of the form C1 alpha 1 to Cn alpha n, that means C1 alpha 1 plus C2 alpha 2 plus so on Cn alpha n, where all the C's are scalars, is said to be linear combination of vectors. Linear span of a vector, linear span of a set. The set containing all linear combination is said to be linear span of a set. Linear combination means we see only one combination of vectors. If the set contains more than one linear combination, we call it as linear span of a set. Let me take a simple example. Find the value of k so that 1k5 is a linear combination of these two vectors. If I take, this is same as L of s is equal to V. If beta belongs to V, then beta equal to linear combination of S. If a vector belongs to a vector space V, then this vector beta can be expressed as a linear combination of S. Here S is a set containing the vectors 1 minus 3. S is a set containing two vectors alpha 1, alpha 2. Alpha 1 means 1 minus 3, 2. Alpha 2 means 2 minus 1, 1. Beta is what? 1k 5. Beta equal to Linear combination of S. Linear combination of S means I have to multiply this vector by a scalar, that is A times of 1 minus 3 2 and plus B times of second vector. Grouping and equating and solving, we get the value of K as minus 8. If you substitute the value of A as 3, B as minus 1, we get what we get? We get 1 minus 8, 5. So this completes the solution of example. Thank you. In the next session, I'll take linearly independent and linearly dependent. Okay. Thank you. Have a good day.